So we're going to find what I'm going to call W max before tipping. So we're given a diagram, and we're told that the floor crane has a weight of 300 pounds, and its center of mass is located at that point G on the figure. We'll call that the weight of the crane, 300 pounds. We have our find, we have our given, so we want to develop our free body diagram. The free body diagram can be just a simplification of this picture. I don't need to illustrate exactly what it looks like. Really what's important are where are forces located, where are couples located on this object. So I really just need a skeleton of what the object looks like. In this, they tell us that they place the origin at that well, the origin is actually not a labeled point here. We have a point labeled C, A, B, and G, and where the barrel is being applied. I'll start by just using the origin that they use. I have wheels at A, at B, and at C. It comes up from the origin and then goes out and over. And then at that end point of the crane, I call it D in my diagram. That's where that weight is going to be applied from the barrel. I'll just call that W, and that's what I want to find the maximum value that can be before it tips. But the free body diagram doesn't need to know that information. Right, so actually I already started with one of the forces that acts on this, the weight of the barrel that it's holding. What other forces or couples act on the crane? I guess I kind of skipped over that step. The object that I'm taking is the crane itself. So I'm not including the floor, I'm not including the barrel, I have to include the weight or the force that the barrel imparts on my crane. But the barrel itself is not in the picture, just the crane. What other forces are going to act on the crane then from supports that I've removed from this? Right, a normal force actually at each wheel, A, B, and C. I'm not including the floor, so I have to include what the floor does to my crane. In this case, it touches the floor at 3 distinct points, each of which could have a different normal force there. And because we're told that they're smooth wheels, we're assuming that there's not going to be any friction between the wheel and the floor. So the only force that the floor imparts on each wheel is going to be that normal force. So we have at B a normal force from the floor. The floor can only push on the crane. We'll have a force up I call AZ. At B, we have a potentially different normal force, BZ. At C, we have a force from the floor pushing up that I call CZ. What's that?
Looks like a shock from the z-axis up
The 30-degree thing? Well, that will be included. That's part of the crane in my picture. So if I'm including it, then I don't include the force that it would impart on that boom arm out top. But you're right, if I did not include that piece of it, then I would need to include I would have like a force here and a force there from that shock. So for simplicity, since I'm not asked for what the force in the shock is, I can just include it here and then I don't have to deal with it. Later on when we talk about frames and machines where we'll have multiple pieces to our machine that we analyze, in that case we might actually want to split it out because we are interested in what the force is in it. But for here, I'll just group it together with the crane. I have those three normal forces. What other force or couple acts on my crane? Yeah.
Center of gravity pulls down.
Right, the weight of the crane itself. In this case, we are going to include the weight of the crane as a force acting on it. We can simplify the weight of the crane acting at its center of mass, which they tell us is this point G. The weight will act in the negative Z direction, and we're told that is 300 pounds. I have four unknowns here, AZ, BZ, CZ, and W, which I don't know. But out of the free body diagram, I will get 6 independent equations out of it. So only having 4 of a very often we have 6, we might want to re-look at this if we were modeling it in the homework or the quiz. But we are going to see that this is correct for our model, as we'll see through the equations. All 6 equations still must be true, and we do want to check that. But this is a good spot to check, did we model everything right? Did we miss anything? Or did we include things that should not be there? The other thing I need here are my coordinates of these points, A, B, C, and D, so that I can correctly do my moment calculations later. Based on the coordinate system, I just used the one that they gave me. B is going to be located at 6, 2.5 at 0 feet. C is located at negative 1, 0, 0. A will be at 6, negative 2.5, 0. And to get to D, we have to go up the vertical boom arm and then out across that 30 degrees. That top boom arm is only in the X direction. So I'm only going to put its coordinates here, but we have to go up the Z. We'll go up a little bit from the 30 degrees, and we'll go in the positive X also due to that 30-degree angle. So if we actually do those calculations, we get in the X direction 8.66 feet. That's really just the 10 feet times cosine 30. And the Z direction, we go up by 1.5 feet, then another 3 feet, and then we go up by 10 sine 30 for a total height of 9.5 in the Z. And point G, where the center of mass is, we'll go 2 feet in the X, we'll go 0 in the Y, and we go 1.5 feet in the Z direction. Now I have all the dimensions of where forces are acting, and I have the forces labeled. So now this will be my complete free body diagram. We can get our equations now out of the free body diagram. So first, usually I start with unit vectors. In this problem, are there any unit vectors I need to find before starting my equilibrium equations? I have AZ, BZ, CZ are only in the Z. The weight is only in the Z, and the weight of the barrel is only in the Z as well. So in this case, everything acts along with a coordinate direction. I don't actually need any unit vectors in order to solve this. Starting with my force equations, I'll start with force in the X direction. It has to sum to 0 because we're in equilibrium. We'll look at all the forces that act in the X direction. In this case, what forces act in the X direction according to my free body diagram? So for my right-hand side, the free body diagram has no forces that have an X component in them. So if I sum the forces, it is just 0. I get 0 equals 0, and while true, it's not a particularly helpful equation to us. But if I did get 0 equals like 300, if there was another applied force on here, if I got 0 equals 300, either my modeling could be incorrect and maybe I missed a support that should have had an X component, or it's possible that it's not in equilibrium and my assumption of sum of forces equals 0 was invalid. So no matter what, whether we're in 2D or 3D, always check all your force equations and your moment equations to make sure you've accounted for everything. So I get 0 equals 0, and that has to be true for it to be in equilibrium. Same idea in the Y direction. Nothing here has a component in the y direction, so I also get 0 equals 0. Looking back at the free body diagram, I counted up here 4 unknowns. Instead of oftentimes we have 6, but we see that already 2 of the equations haven't really given us any information. So there's only going to be at most 4 equations that will give us information. So we could solve for at most 4 variables from the free body diagram alone. An equation that will give us something if I sum my forces in the z direction. All of my forces act only in the z. AZ, BZ, CZ act in the positive z direction. And they have to because they're normal forces. The weight of the crane itself acts in the negative z direction. And the weight of the barrel, which I'm to find in the end, is also going to be only in the negative z direction. 4 unknowns, and really only 1 equation that's useful here, since 1 and 2 aren't going to add anything for us. The force equations in this case are very straightforward since things only had z components. So we have our choice here of which point we want to take the moment about. Which points would make I would say there's not one best choice here, there's a couple ones. What points would be better than other points to take the moment about in terms of reducing how many unknowns we're going to have in these 3 equations we'll get out? Right, A or B or C are going to be your best bet because at least it eliminates one of them. Actually, you could also do W, but since we're looking for W, A, B, or C are actually better bets, I would say. G seems like it would be good because it's the center of mass, but keep in mind if we know the value at G is 300. So eliminating a known 300 from it doesn't actually eliminate a variable. I took it around C. If you go and take it around A, you'll get different equations. That's the only reason I'm going to do it according to my notes. I don't want to try to do this on the fly. Now I have RCB cross BZ. So that's why I have coordinates of B minus coordinates of C. That's where I'm getting here a 7, 2.5, 0. RCA cross AZ. I'll have here a 7, negative 2.5, 0. For the weight of the crane, the negative 300K, RCG is going to be here 3, 0, 1.5. And RCD cross negative W, I get 9.66. Zero and 9.5. All right, so I expand all these cross products or expand all these determinants. And I'm going to move up here so that we can see it. Out of all of this, I'm going to get that negative 2.5 AZ plus 2.5 BZ I hat plus 900 minus 7 AZ minus 7 BZ plus 9.66 W J hat plus 0 K hat. If we look at all of these determinants, the K column, because I have these 2 zeros here, all of the K components are going to be automatically 0. So I actually have 0 K in this equation. So for my equation 6, that also becomes 0 equals 0, taking the coefficient in front of K and equating it to 0. But my equation 5, I get that 0 is 2.5 AZ plus 2.5 BZ. And my equation, sorry, that would be my equation 4. Right, that's negative, this one's positive. And my equation 5, the J coefficient, 0 is 900 minus 7AZ minus 7BZ plus 9.66 W. Equation 3 is going to be helpful, equation 4 is helpful, and 5 is helpful. We found that 3 of our equations just gave us 0 equals 0. We have 4 unknowns, AZ, BZ, CZ, and W, and at the moment we actually only have 3 equations that are not 0 equals 0. So we don't currently have enough equations for all of the unknowns that we're going to have. So what else do we have to consider that we have not looked at yet? What does this tell us about the relationship between AZ and BZ? Right, this is where it is true it's symmetric. So using equation 4, AZ and BZ are equal to each other. If we had assumed symmetry up front, we would have gotten that same result. And if I rearrange equation 5 a little bit here, I'll do it algebraically. I get that AZ and BZ, since they're the same, they're both equal to 64.3 plus 0.69 W. If I plug those values into equation number 3, I won't go through all the algebra here, but I can get CZ is 171 minus 0.38 W. So yeah, if I substitute into equation 3, AZ is 64.3 plus 0.69 W, and that BZ is equal to that. If I rearrange this and solve it for CZ, I get 171 minus 0.38 W. I haven't added any new equations, I've just done a little bit of algebra here. So I can get AZ, BZ in terms of W, and my CZ in terms of W. But I still need a 4th equation, or I guess in total a 7th equation, in order to solve for my unknowns. So where can I get a 7th equation from? As we add more and more weight to that barrel, what is going to happen with the normal forces we have between the ground and our crane? Right, which one do we expect to go to 0? Right, as we put more and more weight on, then less and less contact force should be between C and the ground. So when it's just about to tip, what's going to happen is that just as the normal force goes to 0 between the wheel and the ground is when it's just about to tip, we would expect over that AB axis. If there's no weight on it, if W were 0, then we'll get some positive value for CZ, it's just the normal force. But on the verge of tipping, that normal force drops to 0. And if we apply any more weight on it, then it would actively start to tip because CZ would actually become negative. So what we suspect is happening is when it's on the verge of tipping, the normal force between the ground and the wheel at C is going to be 0. Again, the free body diagram is true for equilibrium. This is going to be true. CZ is still here. It's the equation where we set CZ equal to 0, where we're saying it's on the verge of tipping. That normal force drops and drops and drops. It's just at 0. Now if we look at equation 3a, when it's on the verge of tipping, the only thing we don't know now is going to be W. So if we put this equation 7 into 3a, this tells us that the weight that will cause the normal force just to go to 0 at C is going to be 450 pounds.